Charles' Law, volume versus temperature. I'm Mr. B. Charles' Law is an experimental gas law that describes how gases tend to expand when heated. A modern statement of Charles' Law is as follows, where the volume of a gas is directly proportional to the temperature, assuming a constant number of particles N and constant pressure P. When the pressure on a sample of a dry gas is held constant, the Kelvin temperature and the volume will be in direct proportion. This relationship of direct proportion can be written as follows. V over T is equal to K, or V is equal to KT, where V is the volume of the gas, T is the temperature of the gas measured in kelvins, and K is a non-zero constant. For comparing the same sample under two different sets of conditions, the law can be written as V1 over T1 is equal to V2 over T2. Or simplifying the relationship, we may write T2 V1 is equal to T1 V2. The equation shows that as absolute temperature increases, the volume of the gas also increases in proportion. This illustration shows a graph of Charles' Law, where as the temperature on the gas increases, the volume of the gas also increases, assuming that the mass and the pressure are both frozen. Consider the following practice problem where we're using Charles' Law calculations where T2 V1 is equal to T1 V2. 1 liter of a gas at standard temperature and pressure is compressed to 473 milliliters. What is the new temperature of the gas assuming the pressure remains constant? Standard temperature is 0 degrees Celsius or 273 K, and standard pressure is 1 atm or 101.3 kPa. In this case, T1 will be 273 K. 1 liter is equal to 1,000 milliliters. So in this case, V2 is equal to 0.473 liters. This is because we must divide the 473 milliliters by 1,000 in order to convert to liters. So from the data we write the following, where V1 is equal to 1 liter, T1 is equal to 273 K, V2 is equal to 0.473 liters, and T2 is unknown. So in the solution we may write the following, where T2 times 1.00 liters is equal to 273 K times 0.473 liters. Solving for T2 is equal to 273 K times 0.473 liters divided by 1 liter. In this case, the liters will cancel, and the answer is 129 milliliters. Now for the next problem. The temperature inside of my refrigerator is 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and a volume of 0.50 liters, what will be the volume of the balloon when it is fully cooled by my refrigerator to 4 degrees Celsius? In this particular case, we must convert the temperatures, where K is equal to degrees Celsius plus 273. So in this case, T1 is equal to 302 K. And T2 is equal to 277 K. In the data, we may write the following, where V1 is equal to 0.50 liters. T1 is equal to 302 K. V2 is unknown, and T2 is equal to 277 K. In the solution, we may write the following, where 277 K times 0.50 liter is equal to 302 K times V2. And V2 is equal to 0.50 liters times 277 K divided by 302 K. The Kelvin will cancel, and the answer is 0.46 liters. A soda bottle is flexible enough that the volume of the bottle can change even without opening it. If you have an empty soda bottle of volume 2.0 liters at room temperature, which is 25 degrees Celsius, what will the new volume be if you put it in your freezer at minus 4 degrees Celsius? Let's convert the temperatures first. In this case, T1 is equal to 298 K. T2 is equal to 269 K. So in the data, we may write the following, where V1 is 2.0 liters, T1 is 298 K, V2 is unknown, and T2 is 269 K. In the solution, we may arrange the data as follows, where 269 K times 2.0 liters is equal to 298 K times V2. And solving for V2, we may write the following, 2.0 liters times 269 K divided by 298 K. This represents the numerical setup for solving for V2. The K's will cancel, and the answer is 1.81 liters. Now for the next question. How hot will a 2.3 liter balloon have to get to expand to a volume of 400 liters? Assume that the initial temperature of the balloon is 25 degrees Celsius. First, we convert the temperatures, where in this case, T1 is equal to 298 K. And T2 is unknown. In the data, we may write V1 is 2.3 liters, T1 is 298 K, V2 is 400 liters, and T2 is unknown. In the solution, we may arrange the data as follows. T2 times 2.3 liters is equal to 298 K times 400 liters. Solving for T2 gives the following. T2 is equal to 298 K times 400 liters divided by 2.3 liters. The liters will cancel, and the answer is 51,826 degrees Kelvin. This concludes my explanation of Charles' law. Hopefully this video has been helpful.